we can't get this sorted out. So let's see if we can all see me. Yes, we can. Awesome. All right, wait another minute and then we'll, I guess, begin. First, can everyone hear me okay? Let's go with that. Um, but it looks like it should be popping up. Yeah, all right, so we're good to go. I had to make a slight adjustment to the schedule because Google Colab wound up kind of breaking class confusion, which I wasn't really expecting to have happen in the last few weeks. Specifically the tabs don't actually show up. So I need to look into that because that's kind of one of the major benefits of class confusion. So instead, with sort of going in the theme of data loaders and inference and whatnot, I'm going to show you guys how we can modify the FastAI data loader to accept vision and tabular inputs, but this is any sort of multimodal model. If you've seen my article, then we're just basically going to be walking through that. And then we're going to cover feature importance and waterfall plots, one of which was implemented by a FastAI user, Pavel. And we're just kind of going to go with that. And then next week we'll explore some more tabular interpretation within class confusion and sort of see what happens from here. But I wanted to show this because it's an important concept and I wanted it on video somewhere for people to use along with the article and the Kaggle kernel. So for those of you reading the chat, I linked the Kaggle kernel. However, in the Practical Deep Learning for Coders 2.0 repo, it is just called Mixed Data Loader. Also, I am in the midst of working on the text notebooks. We'll go with that. So I'm not going to put an ETA on it, just it's in the works. But otherwise, let's just go ahead and jump into the lecture. So the main challenge with dealing with multimodal is you got to worry about how your inputs are coming in, how they have to play with the FastAI transforms. You know, do you make a separate transform for each one? And I went a little different approach. Instead, I kept everything the same and just tried to combine two data loaders because worrying about the transforms is hard enough. If instead I just build, say, a tabular data loader, a text data loader, and a vision data loader, and I somehow wrap them all together, there's no real overhead except for what we're going to go over today. So this is the SIM ISIC melanoma classification Kaggle competition. And we're not going to go into the model aspect of it because multimodal models are a bit more difficult to handle. Instead, we're going to focus on the data loader aspect of it. So the general approach for doing this sort of thing is they all need to share three functions. One batch, shuffle function, and a show batch function. This is essentially, for the most part, all you need for this to work. So in this sort of kernel, we're going to open up the, hey Lucas, so we're going to open up the training data frame, which as you can see has it's a little bit of background information about each person along with an image name. So we'll make a tabular data loader for this metadata, and then we'll make a vision data loader for the images. Now I'm just adjusting right here what the paths I'll go to. This is just specific for the data because I want this to work with test data loader as well. So the tabular data loader is pretty much what you would expect. You pass in your columns, you create your tabular pandas object, and then you pass in a batch size. And I'm keeping the seed 42 right now. This actually isn't needed because what will wind up happening is I'll get the same shuffle function, but this is just for reproducibility. Now vision, it's again, we create the same sort of data loader ask. We're using PIL DICOM because they are DICOM images I come in with, but again, this is not specific. Based on what you use, any sort of input will do. And then we just build some data loaders. And if we look, so the first one here is a transformed data loader. So hypothetically, if we split all of these the same way, then we would expect our training set to be the same and our validation set to be the same. And that's very, very important. So now let's look at our mixed data loader. It's not going to be a data loader in itself. It's a data loader of data loaders. Not to be confused with data loaders. That's why I called it mixed data loader. Makes it nice, easy, and simple. And we'll sort of go over what you need to adjust based on how many inputs, what those inputs are, etc. So FastAI has this fake loader. This is sort of a way for you to quickly get access to your items during training. So that's something we do need. But otherwise, the first thing we do is note down what device we're using. And then we're going to override the shuffle functions here with a new shuffle function. Now, what this needs to do is we take, essentially, at the beginning of every iteration in your data loader, if it's training, then it's going to shuffle everything. And so what we need to do is tell our data loader that if we need to basically keep track of how many times we shuffled. So when I just said we'll just have a count of 0, and if we have a count of 0, we can generate a new RNG, which RNG is basically a list of indexes that we're going to slice into each time we call a batch. That's how the shuffle function works with FastAI. And we only want to generate that once every 2, because the other data loaders, in this case 2 data loaders, need to use that RNG. So if you had, say, 3 or 4, then you would do, you would have 3 of these or 4 of these if count is 0, count is 1, etc., etc. That way, it's only shuffled once, and that same shuffle is applied to all of your data loaders. And then we have 2 because that is needed, and all it does is just override our device. And then lastly, just some way to store your data loaders, so I keep them in an array. So the shuffle function is the first thing that is sort of data dependent, specifically by the amount of data loaders you're working with. And so if we look, so if we call get indexes, this is what I was talking about. So the first batch in our vision data loader, we'll call it this index, this index, this index, and this index, and so on and so forth. And the tabular, we'll call them at these indexes. So the way that we test if this is working is we make our mixed data loader, and then we check each data loader inside that mixed data loader for their indices. And you can see here that they're exactly the same. Now you probably noticed I didn't pass shuffle here. That's because you want to take care of that in the internal data loaders. So whenever you're building your data loaders here. This is not an option you set. If you want to, you can, but considering how this pipeline is taken into consideration, I personally wouldn't, because by that point you already know if it's shuffled or not. All right, so now we need to grab a batch of data. And this is going to look a little scary at first, but we're going to walk through it together. So essentially, what we're doing here is for every batch in essentially my data loader, for every data loader essentially in these, we zip up our data loaders together. This is actually, this line right here, this loaders fake I, is directly from the one batch from fastai2. So just roll with it personally. So we're going to zip up all of our batches. And then for each batch, first we're going to check to see if they are in our device we want or not. Because basically at this point, we have applied our type transforms and we have applied our item transforms. We have not applied our batch transforms yet. So that's what this step is doing. So first we're going to take all of our little mini batches from Z, set it to whatever device we want, and then we're going to build a batch. So here I'm taking, in this case, the tabular data loader was my first data loader, and it outputs a categorical array, a continuous array, and then Ys. I only care about the categorical and continuous here, so we're going to extend with both of those. And then I want my image, so we'll also append the image, which is batch at 1, 0, because it's only image, and then label. And we're specifically also going to apply the after batch to those items. And then finally, we just have a check here that basically says if our data was labeled, then we're going to add that Y in. Otherwise, we won't. And if you notice, it's kind of just boom, 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 boom. We don't necessarily keep track of an array of X's and an array of Y's. fastai internally can figure out how many of your inputs are your X's and how many inputs are your Y's. So next thing we need to do, now that we have all of this, so let's sort of go into an example of maybe things would be a little different. If you wanted to instead grab the Y's from here, right here, this would be 0 and 2, for instance, because that would be your last one. There's a million different ways that you can refactor this. This is just sort of something I came up with very quickly. It can certainly be improved, but it does the job for me and kind of gets you to understand what we're doing, and so that's why I enjoy it. And that's why I like using it. Now, the one batch, we're basically taking our data loader and doing what's called fake L no multiproc. All this says is it sets our num workers to 0. So that way there's no bits of multiprocessing going on that could cross wires. And then first grabs the next iterator. So first is literally equivalent to next iter data loader and grabs a batch. And then finally, if it has a iterator property to it, we just want to delete it because we don't necessarily need that. It's already an iterator in itself, and so we just call next on it. Now, occasionally, you might get this exception ignored generator in the iterator. I haven't found that that causes issues. I don't know necessarily where that stems from, but you can just ignore it for right now. Now, if we look at our batch, we have our categorical, we have our continuous, we have our tensor DICOM, and then we have our tensor categories. And so now we can successfully grab all our data. And that really wasn't all too bad. The only bit that took consideration was this iterator. Also, if those of you are confused by this @patch syntax, this is sort of a lazy way for you to find classes sort of split up into notebook cells. I like it because sometimes I don't need a function until much later or whenever I'm thinking about it. And so you just set whatever you want your input to be, and you specifically set the type. And what this will do is literally patch this iterator function to this mixed data loader. All right, so we got almost everything, right? What's the last thing we need? Well, we need to show a batch of data. So that's probably the easiest one of them all. All we really do is successively call show batch. You could get into this and maybe link all of the batches together in some form, but sometimes lazy way is the best way. And in this case, it kind of is because it's not really too bad to look at. And you can see that each of them correlate with what the other one is. It's a lot harder to see in this example because everything is 0, but that's okay. Now, the last thing I want to show is how you do inference with this mixed data loader, because we didn't give it a testDL attribute. So since it takes in 2 data loaders, we just pass in 2 test data loaders. So we just simply do, for instance, image test and tab test, testDL, pass it to the mixed data loader, and that's all that's in there. Because remember, we had an if statement that would take care of if no y's were there at all. And so now, if, for instance, you wanted to use fastinference for this, all you have to do is specifically set your number of inputs in learn. This is not something that I did. Might need to do it, but you need to set number of inputs based on how many inputs you're expecting, and then you can just call getPreds, and it works exactly like you would expect. And it also works in regular FastAI as well after you set this attribute. So for those of you that have joined, is there any questions regarding this technique and sort of the decisions I made along the way? All right. If not, then let's go into some funner stuff. More fun is not a word, we're still going to say it's a word. So let's go into feature importance and dendograms. Now, I'm very excited and thankful that a fellow FastAI user by the name of Pavel has really been shaping how we do this sort of interpretation in tabular neural networks. All of this is pretty much his design. It's not, ported from any code. So is it used to like having the image mixed with the data, the CSV? Yeah. So like the whole point of this is this is just the data loader part. It's not the model part. You guys have to sort of figure out what to do with this multimodal data loader. Google just published a paper, I believe, no, it's Facebook, about the difficulties in training such a model, but they did come up with a solution. However, yes, it's a way for you to sort of train one model that takes into account both your image as well as any sort of context around it. So a good example is there was a pet adoption Kaggle competition, I think last year, maybe it was a few months ago or so, 6 months, where you had a image input, you had a text input, and you had a tabular input. And so people wanted to know how you could combine all of those together. And this is one way to do it inside the FastAI2 framework with no real issues whatsoever. Now, when it comes to a model perspective, that's where things get a little more tricky. You could, have maybe a ResNet running on one head, you have a tabular model running on the other, you concatenate their outputs. There's a few examples scattered around the forum of such examples, of such techniques. That's the word I want. But I don't really have a guideline as to what to do with it because I've only worked with it a little bit and nothing really sparked my eye too much because the training is very difficult. But for those of you that want to go explore that route, this is the method for doing it. All right, so let's get back to the feature importance in dendrograms. So these are specifically for tabular neural networks. And it's a way to sort of help us get a look into what's going on. For those of you that watched FastAI, Walk of FastAI 2, the tabular portion, the feature importance will look very familiar. However, we're going to go into a bit more besides that here because the library supports it. Also, I will note that this tabular vision isn't directly supported in the fastinference library at all, but it's a technique that I really just wanted to bring up some way in video fashion. So the dendrograms and soon waterfall plots that we're going to get into next lecture were developed by Pavel on the forums. And so all of my code is entirely based on his, if not literally his, and conjecture. So I'm very thankful for that. He has really done an excellent job with these tabular interpretation features and functions inside the FastAI library. This is actually his permutation importance function is where I based mine off of. And so we're going to be exploring that a little bit today. So the initial training, this is just to get us a model that we can explain on. So we'll just quickly make an adult sample and fit for one epoch. We won't worry about learning rates and whatnot. It's just an example. Now, feature importance in this library is based on permutations. Now, what that means is, let's imagine we have my data frame of 3 columns with, say, 5 rows. So what I'm going to do is one at a time, I'm going to take one of those columns and shuffle around those 5 numbers, or 5 variables, or 5 categorical values. There we go. So I'm going to shuffle them around, and so their order, we presume for the most part, is broken, and there's no longer connection in there. Obviously with categorical, if you don't have a lot of categories, it might not do much, but ones that do have a lot of categories, it could. So it's a give and take. But it's that's sort of how it works. So we'll shuffle one column, and then we will measure what its straight up accuracy is. So before we take a baseline of how our model regularly performs, and then as we shuffle each column, we take whatever metric we're looking at, we take what its new metric is, and then perform some sort of difference that we want to look at. That is this perm func that you see here. So base error just means A minus B, so the original minus the new. And then that sort of gives us this permutation importance of how much of an impact did shuffling this one column do to my variables. So what this allows us to, what the library allows us to do is have a new function on our tabular learner called feature importance. Now it'll accept a data frame or a data loader. And this will be specifically what data we're looking at when we're performing these permutations. A perm func, which for right now is base error. And let me see if this instance is still going. It is. We can take a look real quick at base error. And if we look specifically at base error, you can see it's just error divided by value, divided by error. That's actually incorrect. That should be error minus value divided by error, but that's okay, I believe. In any case, so you have this sort of base error calculation. You have the metric we want to look at, and this can be anything, as we'll see. You can optionally pass in a batch size. You can have the option to plot the importance graphs, which we'll look at in a moment, and whether or not we want to reverse our outputs. Now that's important because let's say our metric is mean squared error. Well, the smaller we get, the better we get, versus accuracy, the higher accuracy we get, the better we are. And so that's why this reverse is sort of important. So if we just call learn feature importance, what it'll automatically do is see that we didn't pass in a data loader, and so it'll run off of the validation. And so what this tells us here is the relative change in accuracy our particular mix-up had. And so we can see that in this case, when my metric is accuracy, marital status had the most impact, and the race and relationship had the least. And this also can then be returned as a dictionary. And so what this tells us is if we were to say drop work class, final weight, relationship, and race, we'd be pretty okay. However, if we change that metric to say cross entropy, it looks different. And why is that? Well, cross entropy and accuracy are kind of two different things, because one's our metric, the other one is our loss function. And so they give us two different insights. Not to mention, this should actually be reverse equals true, because with cross entropy loss or any of our loss functions, we really want to get smaller rather than get bigger like our accuracy was. This would be one instance where reverse would be true. And so we have final weight, race, work class, there we go. Now, the attention changes based on your metric. And so, as I sort of mentioned earlier, what you look at can vary the results. For instance, if I look at rock area under the curve, my results might be a little different because the metric operates a little differently. And so what this allows you to do is look at, okay, I have a scenario where I want to examine how accuracy compares to my area under the curve, compared to, say, my loss function, compare all three of them, and see, based on what the target is, how the function itself actually changed, or how my model behaved. And so this will provide a little bit of insight to that. Now, one thing I do want us to do, though, is show us a better example. And so I'm going to define a better base error. So we'll have better base error, where we have our input and our output. So we want to return input minus output divided by output. Because really, this is what that should be. Which if you really look at base error, I believe yes. We'll keep the nomenclature the same. Error val, error minus val, divided by error. And so now, if we do perm func equals there, I believe the results should be a little bit different. Yes, now that's a lot cleaner, and this is what I was expecting. So I'm glad that we went through and did that. So here now we can see marital status had the highest effect. So this is our most important. Whereas race had the least. So meanwhile, let's just pass in perm func actually equals there. This way we're getting accurate information. Now that we reversed it to our loss function, it looks a little different. But our marital status is still the most important. But also notice it goes down by negatives. So it's just a different way for you to read this plot and see what exactly the differences are. And then finally, we'll look at the rock area under the curve, passing in our perm func, which also, the moment this lecture is done, I'm going to go ahead and change the base error that we were using before and make it more like this. Now the other nice thing is, we can obviously see that depending on what metric we're using, the importance differs. And this is something that I believe is a good thing to have in this library because we can go through and examine exactly what's going on. So that's basically all there is to feature importance. That's all that's really going on with this particular technique. And it's not a direct reasoning because there's a lot of, hidden layers and whatnot inside of our model, but it provides a pretty good idea of what's going on. So the last thing I want to show is dendograms and relative correlation. So this will calculate how closely related two variables are to each other. And this was made by Pavel. So we have two new functions on our learn. We have get top correlation dictionary, which this grabs the top pair of correlations in a given matrix on data frame based on some relative threshold. So I'm going to set my threshold pretty low here, for instance, in this first one. And if we try and get our correlation dictionary, what this shows us is that work class and sex are pretty closely related, which, okay, that's a very interesting correlation. Marital status and race are kind of correlated. Education and occupation are the third most correlated. We would kind of expect that. Age and education, and so on and so forth. So we have this one way to get our correlations together very quickly. However, we also have this plot dendogram function. And this will plot a dendogram based on this correlation matrix. However, it's a bit more in depth. So we can see that education num, if it's missing, is related to occupation, which is then related to work class, which then is related to education num, which we would expect that. Relationship and marital status are pretty same, and so on and so forth. So it's a way for us to visually see how our model is doing and explaining its values. Which again is the entire point of fastinference. It's to help you guys with inference along with interpretability. So is there questions on either the feature importance algorithm or on the dentogram algorithms? Which also, I'll just point this out. They are in the documentation. So if we go to Tabular, we can see that we have example usage for the permutation importance, and then I don't believe that I updated it for the dendogram quite yet. I will be doing that tonight because this has sort of all been going on the last few days. But yeah, any questions? Otherwise, that's all that I have for the most part today. We'll also do one accuracy just so you guys can see that. That's why we have debug. Some of the functions work, some of the functions don't. Anything that has a decode shouldn't. So that's accuracy, error rate, and a few others. That's why that error showed up. But all right, if there are no questions, then we will go ahead and call the lecture there. Thank you guys for joining, and I'm sorry that we didn't really go into class confusion the code's not working right now. I got to look at it this weekend some more. But thank you.